Okay, so here is part two of the challenging Cellpose problem. So I've been scrolling through and looking at a few different images and trying out the model I trained on them. It's actually not that bad in a lot of cases. But there's a few weird things like for this image here, I have not been able to detect the whole cell, and even increasing the number of iterations really high doesn't seem to help. So I might in a moment, look into that case in a little more detail. But before I do that, I've kind of thrown um, you into the middle of all this because it's like in my first video, I started talking about the problem. I started talking about how to organize the data, how to view the data, how to draw labels, um, annotations. Um, then I sort of jumped right to a model I'd already trained and showed how to do some predictions and troubleshoot them. But I didn't quite explain how I got to that point of even getting a model. So step back, I'm going to explain that, and then I'm going to take a closer look at this one guy here with the missing piece. Okay, so back to the web view for a minute because it's a little easier to see. Here's the collection of notebooks for this problem. So I've been looking at this Explore Data notebook where we bring up the Napari viewer with a special widget into it to look at like the entire sequence of data and the labels. And then so to actually generate the model, there's like these other three notebooks I use: Make Patches, Optimize Training, and Cellpose Training. So back to the Visual Studio code view, which is a little harder to see, but let's just quickly go over what these do. So this Make Patches notebook, it loads in the labels, bit of code here, bit of glue code to find the labels in the right spot and just make sure they're looking okay. Then it normalizes the image and augments the labels to create these patches. Normalization, it's actually a tricky thing. When we do this stuff, we have to make sure that we normalize on both ends, sort of the training end and the prediction end. If not exactly the same way, at least not in a completely different way. And for some problems, it actually sometimes even makes sense to use like larger normalization ranges than you find in the training images, because the images you eventually predict on might have larger ranges um, than the ones you trained on. And sometimes you can address that a little bit through augmentation as well. So this notebook generates a bunch of training patches, and we can look at these in the File Explorer. You can see there's some just variations of the same label, a little bit of intensity variation, which hopefully makes things more robust. And as I said before, this step is often hidden. So this step is, again, a lot of times maybe it doesn't make sense to waste so much disk space on all this. But again, sometimes useful and to look at for some troubleshooting. So that's the way I usually do things. That's to make patches. Then for this problem, I had a notebook here called Optimize Training, and this one is kind of interesting because this guy, I actually do a little trick here. So what I do is I train a model, totally overfit a model to one image, and I do that really because I want to test whether the model is actually even able to like code the image structure. In the one case where, like, if you train on one image, it's just memorize that image, and if it can't do that, it might indicate that like the design of your neural network, or the way you're approaching training, maybe is some of the parameters are wrong, and or maybe the approach you're using can't even fit like the data you want it to. So in this, the whole entire goal of this optimized training with self prediction is to predict on train on just this one example and see if I can get it perfectly. So basically what I did is I just replicated this training image to make a training set to sort of minimize some of the randomness. Because if I actually literally show it one image, Cellpose internally, remember I keep talking about this inline augmentation, Cellpose will internally do the inline augmentation. So every image that's presented is a little bit different. And then then at the end of each epoch, it's a little bit random because it only saw one augmented image. So if you give it like 100, it evens out a little bit of the randomness, I think. But it's 100 of the same image. And then I just train it. I've trained it a few different ways, a few different settings. One of the settings here I've changed is the rescale. So for some trials, I put rescale is false. And then I've actually done the B size as well, which is something I thought was important at first, but now I'm thinking, especially based on a little feedback from Carson Stringer, the author of all this, she says that maybe this one has to be used with care. So I'm not as convinced B size is that important. But the rescale still probably important. So I train a couple of different models, varying the settings a little bit. And the goal here is to just try to get a perfect answer because I'm then going to test it on the same image, the same one image I trained on. So here I go through a few of these. For example, the first thing I did is try to predict it with Cyto3, and you can see it's not really getting the protrusions. And then I'm also outputting, so in these little plots, Cellpose actually predicts probabilities and flows, and then the masks are generated from those artifacts. So I'm actually in these little plots doing ground truth, prediction, then the probabilities and flows. So the first one is Cyto3. Then the second one is like retrained with just the default, like not really tweaking the training settings at all. And now here is a nice piece of information. Just retraining on while drawing these protrusions a little better does make a pretty big difference, I think. So it's actually with default Cellpose settings, it is finding more protrusions once I redraw them. And we can look here at the probabilities and the flows. And they're a little bit fuzzy because of the rescaling. So with the default settings, these images are probably rescaled inside the training during the training process. And then when you actually evaluate, since they were rescaled during training, you have to rescale during evaluation, and you do that by increasing the diameter a bit. Another option is to train with the rescaling false. And there's a kind of a point, which is still actually a little bit confusing to me. So it's another thing to make sure if you're following any of these videos, make sure you don't believe anything I say and always get like a second opinion, go to the forum. But what I've been finding is that when I train these networks, if I put rescale equals false and it doesn't do rescaling during training, then during prediction, I always have to use diameter equals 30, which seems kind of weird because obviously the diameter of these images is much bigger, but diameter equals 30 seems to, so if you want to stop rescaling during training, you put in rescale equals false. And if you want to stop rescaling during evaluation, put diameter equals 30. And I'd love to hear more feedback about this if I'm just hacking and there's a better way to do this. But with that combination of rescale equals false during training, diameter equals 30 during prediction, then I get, if you look here, I start to get probabilities that are much sharper. And you're seeing a little more fine structure in the prediction as well. So you can see this with the defaults, you're missing some of the protrusions, and then you turn the rescaling off, and you're getting some more additional protrusions. Um, yeah, and then you see I also have used this annotator. I've been talking about this a bit. Putting this at 2000 also seems to help. Yeah, so then once you figured out like, okay, maybe I know the best training settings, then I have just this training notebook, which is mostly just file manipulation code. It basically just loads up all the patches. All my code sort of expects things to be organized in a certain way. Um, so yeah, if you like to organize things differently, of course, hopefully this is just more of like an inspiration of some strategies to use, and you can do some of your own notebooks and everything to get code the way to get your images the way you like to organize it. But anyway, this is just grabbing all the images, then running the training with some of the settings that I uh, found from Notebook 30. Okay, and then Notebook 38 is um, it's similar to Notebook 30 in a way. It was optimized training. This is optimized evaluation. So I load in images and I just test the predictor on it while also trying to optimize some of the settings. And if you look at this image here, this is the one I was looking at Napari before at the beginning of this video where we're missing this section here. And I was just playing with it a little more to see if I could try to fix that. So what I've done here is I've loaded in my model, loaded in the image, then I've evaluated it. I'm using like a ton of iterations, and I'm also plotting the probabilities and the flows, and they both look okay for this one. So wondering a little bit exactly what's happening. Maybe because I'm hacking around with the diameter and stuff, I'm like using the diameter in such a way that I'm trying to stop the rescaling from happening, but maybe that's causing something else to happen because like if you look at the probabilities and the flows, they both look good for this one object that we haven't quite got. But yeah, so this is still a little bit of a mystery that I'll hopefully with the help of the forum and try to figure out in the next few days. And then other than that, this last is also a batch process notebook here, which is kind of useful because it generates, if we look here, it generates like a bunch of overlays. So yeah, so you have all these images with the overlays to quickly present them to other people and stuff. And so yeah, so that's I think that's it for the notebooks for this problem. Yeah, I plan on discussing this problem further in the next weeks, and it should be interesting to find to see like what optimal um, um, you know like what strategies there are to make this even better.